anti-reflection coatings. So we're going to talk about two topics, as I said. But now, what are anti-reflection coatings? Now, first of all, anti-reflection coatings are very ubiquitous everywhere. The glasses I'm wearing have anti-reflection coatings. The windows of your homes, the windows of your automobiles, the display on your cell phone, the display of the LCD that I'm using, all of these have anti-reflection coatings. So, and of course, there's lots of optics involved in these anti-reflection coatings. So this is useful for us to think about. And in a solar cell, of course, this is a critical problem, right? So we kind of thought about this before, but let me try to illustrate this very briefly. So first of all, let's imagine a solar absorber or a solar cell, for the sake of argument. Let's imagine lights coming into the solar cell, that's from the sun, right? Now, we want 100% of the light to essentially go into the solar cell and be absorbed. But unfortunately, we do know that some of this light essentially will bounce off. And this is referred to as the Fresnel reflection loss, right? And you saw this when we talked about the loss of reflection. Now, this is a problem, right? You want to minimize this as much as possible because this is essentially lost. It doesn't enter the solar cell. So it's gone. So you really want to minimize this. That is the purpose of the ARC. Okay, that are anti-reflection coating. I'll refer to this as ARC. Okay, so with that, let's jump into. So you can see why this is important. We want to. Sorry, I should also say one more thing. The anti-reflection coating is essentially a coating you put on the solar cell here in order to achieve this, to get as much light into the solar cell as possible. And of course, it is true for windows and anything else, right? Okay, so what is anti-reflection? So you can see very simple examples here. So here is an example where you can see the scene the person is looking at is reflected off her glasses, because there is no anti-reflection coating here, right? It's acting like a reflector. Whereas here, there's an anti-reflection coating and you don't see the reflection. Obviously, this is better for clarity of vision, right? Because you're not losing light. And there are a few more examples here. You can see the example of some deleterious reflections here, which are missing here, so that's good. Use a different color. Here, anti-reflection can also be anti-fogging as well, so that's the example shown here, and this is, you're missing that. So for those of you who ski, obviously, you're probably very familiar with this. Again, you can see that here as well. Now, this is another interesting problem. In fact, I was in a meeting, interestingly, earlier today, where we were talking about this particular problem in the case of contact lenses. So when you design contact lenses, if you don't have appropriate anti-reflection coatings, you will end up seeing this kind of a problem, which is a halo, right? So by designing the coatings properly, you can actually avoid this. So again, that's a good example for human vision. And you can imagine similar sort of problems for cameras and things as well, right? Now, how do we go from here to here? Like, what can we do? We can design a coating to prevent that reflection, okay? Now, the halo problem is a little bit different, but anyway, we can assume similar things. So this is exactly what we want to do. We want to have 100. We have 100% of the light coming in. So let me change the color. And we want to have 0% bouncing off, right? Nothing bouncing off here. That is what this AR coating will do. You want 100% of the light essentially going in to whatever it is. That this can be a solar cell, this can be just your eye, this can be a camera, whatever. thermal absorber, whatever, right? Doesn't matter. We are agnostic. Now, if you don't have the AR coding, you will get this loss. And typically, if you do the analysis, it's at least a 4% loss. Hold on, Ikata, let me make you the co-host. Okay, good. So intuitively, the way to understand this is the following. The reason you're getting the reflection is because of the refractive index mismatch between the air, which of course has a refractive index of 1, and whatever it is that you're trying to absorb into. Let's say if it's silicon, the refractive index of silicon is about 3.5. Now, this mismatch between 1 and 3.5 is what's causing this kind of a reflection. So you try to minimize that mismatch. So you try to design a coating which has a refractive index in between. So in this example, they're taking a geometric mean, which is a square root of the product of the refractive index of air and the refractive index of glass. In this example, they use glass, so I can use glass as well. In that case, it's 1.5, right? Something like that. Okay, so, and the other thing you try to do is you try to make the thickness of the coating lambda over 4, and we'll see why that is in the next slide. So the quarter wave coating, which is what I was just talking about, that the thickness of the coating is lambda over 4. This is what the quarter wave coating. In order to understand this, we need to understand a phenomenon called interference, which we haven't talked about. Okay, interference is a phenomena that is ignored in geometrical optics. So in this class, we focused on geometrical optics. We ignored things like interference, diffraction, and so on, which is in the regime of diffractive optics. Okay, or physical optics more generally. So we need to understand what the interference means. Now, light, as we know, is composed of waves, right? We talked about that briefly. So if I have a wave, and if I have another wave, which is in synchrony with it, then if I add them together and they're perfectly matched like that, then I can get a wave which is twice as tall. So if this is 1 and that's 1, I can get 2, right? So this is called constructive interference. And analogously, I can also have a situation where I have a wave and I can have an opposite wave. This is a wave that is 90 degrees shifted, right? This wave is shifted in this direction relative to this wave by lambda over 2, right? Because the peak here now corresponds to the dip here. The dip here corresponds to the peak here. And what happens here? I will get nothing. It'll be 0 because everything will perfectly cancel out. This is called destructive interference. And this is called constructive interference. Okay? You take advantage of this idea in order to design the anti-reflection coating. Particularly, you try to take advantage of the destructive interference because you try to ensure that what the reflected light is out of phase by lambda over 2. And if you do that, you end up with a situation that the reflected light is now 0 and 100% of the light is transmitted if it's a non-absorbing material. Okay, so let's actually take a closer look at what that means. So I'm going to play a short video. Actually, I guess, let me see if there's sound. I can't remember actually. Oh yeah, there is sound. So I'm going to try to share again. Hold on 1 second. Share again with sound. I forgot to do that.
Interference. You'll notice at the bottom of the screen video and in this
First of all, can you hear the sound? Got that?
Yes.
Okay.
video animation, we will be able to see constructive and destructive interference. You'll notice at the bottom of the screen that we have 2 waves, wave 1 and wave 2. Each of these waves has the same amplitude of 50 units here are irrelevant. And the picture above here shows us what the two waves look like when they're added together. And so let's see what happens when we change the relationship between these waves. If I move the waves so that they are in phase, the amplitude of the wave, the resultant wave, increases. So now the amplitude is very large. If I come down and I start to move them so that they are out of phase, we can watch the top of the graph, and we can see that the resultant of these two waves, when they're added together, starts to change. And so it gets smaller and smaller and smaller. Eventually, when they are exactly out of phase with one another, the resultant is that we get destructive interference, and we have a resultant wave of 0. So when they are out of phase by 180 degrees, you get a resultant of destructive interference with 0 amplitude. And if we move it back up to where they're in phase, the resultant is that we get constructive interference and we get the maximum amplitude.
Okay, good. So that makes sense. Let me hit this. So again, just to clarify, they talked about 180 degree phase shift here, right? Oops, my thing. So they talked about 180 degree phase shift for destructive interference. Now 180 phase shift corresponds to half the wavelength. So again, if you think about the wave, if I take that wave and move it, so this is one wavelength, right? This is lambda, and this is half the wavelength. Now, if I shift this wave by half the wavelength, what happens? This is 0, becomes peak, so peak comes here. I will get something like that, right? Actually, no, it should. I didn't move enough, sorry. Let me redo that. This is quarter wavelength. This is another quarter, so I got to move it by half. So this dip now corresponds to the peak, as I showed before. So I was right before. And goes down, right? This is 180 degrees or lambda over 2. So this minus value adds with this positive value and becomes 0. 0 plus 0 becomes 0. This minus value plus this positive